Hello everyone. In this session, let me start with Unit 2, where the first concept is power series. So before getting into the topic, let me revise the basics which we need to know in order to prove the theorems whatever we are going to study in this unit. So first one is sequence. So as you are familiar with this word sequence as well as series, but anyhow let me repeat it once again. Sequence is none other than, in general, before going to sequence, any complex number or a complex plane is represented by C or something like this. Fine. Now, sequence of a complex number is a function which is defined from a set of natural number to a complex number. I'm just repeating once again. Sequence of a complex number is a function which is defined from a set of natural number to a complex plane C. Fine. And we write that as a of n is equal to an, where all the elements of n is in n. Fine. Now, we usually denote sequence as an from n is equal to 1 to infinity. Why? Because sequence in the sense it contains infinite number of series. Or we can also say a sequence is none other than a particular set of numbers, say a1, a2, a3, so on, infinite number of elements we have. So that kind of elements which is arranged in particular format or in certain format is called as sequence. So first term is represented by a1, second term is a2, third term is a3. So in general, a sequence of nth term is represented by an, where an denotes the nth term of a given sequence. Clear? So this is the basic definition of a sequence. Fine. I'll just give you one example. 1, 1 by 4, 1 by 9, 1 by 16. You can note that here the numbers are arranged in the form of squares. That is 1 by 1, 1 by 2 square, 1 by 3 square. So in general it is 1 by n square. This is the nth term of a given sequence. Fine. So I can, from this definition, it is clear that n is a sequence and it is defined as, in the nth term of this particular sequence is 1 by n square. Fine. Now, this is the usual definition of a sequence. Now, let me define the same in terms of complex number. Fine. So, let a sequence an be in a complex plane. If a sequence an is in complex plane such that an element a belongs to complex number c, then we say that an is converging to a. This is the definition of convergence of a sequence. An is converging to a as n tending to infinity if there exists for epsilon greater than 0 and n naught such that an minus a is less than epsilon for all n greater than or equal to n. So you already studied the concept of convergence of a sequence in your UG classes. So I'm extending the same concept for a complex plane. So a sequence an is said to be converging to certain value a in a complex plane C, that is represented by an is converging to a as n tending to infinity. Then there exists an epsilon greater than 0 and n naught greater than 0. Greater than 0 in the sense positive numbers in such a way that difference of those numbers will be less than epsilon. Fine. Or else we can write this as an belongs to set of natural number over epsilon of a. So we can represent the same as this. Fine. So now onwards, wherever I have a concept of sequence, so I can apply these definitions. So you have to remember this concept. Fine. And now let me say some key points for you to remember. Suppose if I have limit n tend to infinity an, then we can write this as a, as an converging to a. Definition of convergence. If an is converging to a, we can write limit n tend to infinity an is equal to a. This is the basic definition which you already studied. Just it is a recapitulation. Fine. And the second one is sequence which has a limit is said to be convergence. In the sense, suppose if I have a sequence an, suppose if a limit of this sequence exists, then this sequence will be convergent. That is, for any sequence, if a limit exists, we can say a sequence is convergent. Fine. And one more thing is that a sequence which do not converge is called divergent. Right. The opposite of convergent is divergent. If it is not converging to particular value, we say that sequence as divergent. And suppose if limit n tending to infinity, an is equal to a, meaning is that in place of a, what we have a. So meaning of this statement is an converging to a. Here an is converging to infinity. That's all. Fine. Whatever may be the value you have, so that sequence converging to that value. And it can be seen that limit of a sequence exists. If limit exists, then that value should be unique. Where you have already solved a number of problems in a sequence and series of your UG classes, where you have studied this theorem as well, right? If limit usually does not exist for a sequence. If it exists, then that should be unique. That is, limit of any sequence is unique. Fine. Now, let me explain one definition. Suppose if I have a sequence Zn, which is said to be Cauchy's sequence. When do we say, so we are now, so for whatever studied, it is comes under a concept of sequence. Now, let me say Cauchy's sequence. Cauchy's sequence. We say this as fundamental sequence also. So one and the same. Cauchy's sequence is also same as fundamental sequence. So it is represented by Zn. So Zn is said to be Cauchy's sequence whenever there exists an epsilon greater than 0 and for any positive integer n, positive in the sense greater than 0, such that magnitude of Zn minus Zn is let me say m. Zm, magnitude of some value Zm minus Zn is less than epsilon for m and n are greater than n naught. N naught is one of the number. That is whether it may be natural number or any kind of number. If Zn is said to be Cauchy sequence only if it satisfies this condition. So why I am explaining all these things, I am going to use all this property in the whatever the theorems that I am going to prove in this lesson. So you have to remember all these properties. Fine. So this is what the concept of sequence is. Now let me explain the concept of series. And anyhow you are already familiar that with the word series. So coming to the complex numbers, series is none other than, suppose if I have a sequence say an. Fine. Series is sum of the sequence is called as series. So if I have a sequence an in a complex plane C, then a1 plus a2 plus so on. In the sense, whatever the elements you have within this sequence, if you are going to take sum of all those elements, we will get an infinite series. That's all. A sum of all the terms of a sequence is none other than series. Simply, suppose if an is sequence, whatever the elements you have within the sequence, if you are going to take sum of all those elements, you will get an infinite series. And usually it is denoted by summation k is equal to 1 to infinity ak. So it denotes an infinite series. Fine. Now, and similarly, suppose the sum, usually Sn denotes the sum of a series. So Sn is a1 plus a2 plus so on plus an, where n is equal to 1, 2 and so on. So this sequence, sum of the sequence Sn is called as partial sum. Fine. I am just repeating once again. Partial sum. See here, suppose if I have a sequence, when you are going to take sum of all those elements, you will get an infinite series and it is represented by this using summation symbol. Now Sn denotes the sum of all the terms of this sequence. I mean elements of this sequence. Or else we can say this is a series which is finite. So if you are going to take sum from n is equal to 1 to infinity for a given series, it is called as, it is represented by Sn. So it is called as a partial sum. Fine. And further, sum of the series is none other than, suppose if limit n tending to infinity, Sn is equal to S. So this is what the definition of convergent is. Meaning is Sn converges to S, right? Then S is the sum of the series. S is said to be sum of the series. Difference is that whenever I have Sn, n is equal to 1 to infinity, it denotes the partial sum, but it not contain all the elements. Suppose when I have limit n tending to infinity, Sn is represented by S. Here S is called as sum of series and it is represented by summation of all the elements of a sequence an. N is equal to 1 to infinity an. So it is represented by this. So this is called as sum of the series. This is called as partial sum. So don't worry, I'll just send you the notes of all these summary whatever I am explaining today. So all these things are basics. Moreover, it is in your syllabus also. So you have to go through these concepts once. Fine. Next concept is convergent. Convergence. Now, as you already familiar with this word, suppose if I have a sequence an, when we say the word convergence, it is with reference to sequence only, right? Suppose if I have a sequence an which is in a complex plane. Complex plane in the sense the elements of the sequence will be of the form x plus iy. That's all. So complex number. Then the series summation an, that is n is equal to 1 to infinity, is said to be absolutely convergent. Is said to be absolutely convergent if and only if summation n is equal to 1 to infinity, absolute value of an is convergent. I'll just repeat once again. As I said, AN is a sequence. So a series, when do we say a sequence becomes series? When you're going to take sum over all the elements of a sequence. So here is a sum of all the elements of a sequence AN. So this represents a series now. This is a sequence of a complex number. Fine. Now I'm going to take sum over all the elements of this sequence. So it represents a series now. So this series is said to be an absolutely convergent only when the individual elements of this series is convergent. That is what the meaning is. Absolute of this AN is convergent. So this is the definition of convergent. Fine. Now we have a simple theorem based on a sequence. Anyhow, it is also there in your UG class, but again it is repeating. So every convergent sequence is a Cauchy sequence. So as I already told you, Cauchy sequence is also called as fundamental sequence, and by explaining the definition, while explaining the definition, I have explained this clearly, right? Cauchy sequence in the sense it is represented by Zn. For a Zn is said to be Cauchy sequence if there exists an epsilon greater than 0 and n greater than 0 such that magnitude of Zm minus Zn is less than epsilon where m and n are greater than some values n naught. Fine. So this is the definition of Cauchy sequence. Now what I'm going to do is I'll just take every convergent sequence is a Cauchy sequence. Now let me take a sequence is convergent and let me array that it is a Cauchy sequence. Fine. So let me take, let Zn be a convergent sequence. Let n be a convergent sequence. Fine. So when I said it is convergent, it should converge to certain value, right? So let me take Zn converges to Z0. You have to write it in a proper sentence format, but just I am explaining the concept. So let me take Zn converges to Z0. Now let me write the definition of convergence. So as I already explained, so if Zn converges to Z0, then there exists an epsilon greater than 0 such that magnitude of Zn minus Z0 is less than epsilon I have. But here let me choose epsilon by 2. So as we are already familiar that whenever we are going to choose epsilon, since epsilon is arbitrary, it is very small. So we can manipulate the value of epsilon as per the requirement of the theorem or a problem. So here let me choose instead of epsilon by 2 for all n greater than or equal to n naught. Hence if m certain value, take m which is greater than or equal to n naught, this value, and n greater than or equal to n naught. This convergent condition is true for all the elements of n which is greater than or equal to n naught. Now let me take, if it is if for all n values is greater than or equal to n naught, then let me take one more variable, say m and n which is greater than this value. Then I can write magnitude of Zm minus Z0 is less than epsilon by 2. Why? Because see here, for all n greater than n naught, I can write this condition is true. In place of n, what I have chosen, it is m. So in place of n, I have to replace it with m. Fine. Let me take this as equation 2. Fine. Now let us consider Zm minus Zn. I can rewrite this term as, see here, I am going to write this first term as it is. Now I will subtract Z0 and add Z0. Just to apply this property, what I am going to do is I will just subtract Z0 and add Z0. Again last term I am going to return as it is. Fine. Now this can be written as, it is a magnitude, right? So when I am going to split magnitude, equals will become less than or equal to. Fine. So I am going to group this as Zm minus Z0 plus Z0 minus Zn. Now as from the equation, let me take this as equation 1. Look at equations 1 and 2. So it is a Zm minus Z0 value is less than, so less than or equal to will become less than epsilon by 2 plus epsilon by 2. So when you add this, you will get epsilon, less than epsilon. That is magnitude of Zm minus Zn is less than epsilon. Now we can clearly note that since Zm minus Zn is less than epsilon, so as per the definition of Cauchy sequence, what is the condition? If magnitude of Zm minus Zn is less than epsilon for all m, n greater than or equal to n naught, this is what the condition is, right? So m greater than or equal to n naught, n greater than or equal to n naught, and moreover this condition is satisfying. Therefore we can say a sequence Zn is convergent. See here in this session I have explained this concept. That's why I am showing all these definitions for you for your reference. So in the next session I cannot show you again and again. So you have to remember all this concept. I'll just try the statement and I am going to the concept straightforwardly. So as this satisfies the given condition, I can directly write that Zn is convergent. Zn is Cauchy's sequence. Zn is Cauchy's sequence, and that is what we need to prove is, what I have assumed is it is convergent, what I have proved is it is Cauchy's sequence. Clear? Now, from this theorem, we may conclude that a sequence in a complex plane C is convergent if any sequence in a complex plane is convergent if and only if it is Cauchy's sequence. Right? So it is one of the criteria for any sequence to be convergent. When do we say a sequence is convergent? When it is Cauchy's sequence. Or when a sequence is Cauchy's sequence, it is convergent as well. So this is called as criteria for convergence of a sequence. It is also called as Cauchy's criteria for convergence of sequence. Cauchy's criteria for convergence of a sequence. Fine. So this is almost 90% of this session. You have already familiar with this. Why? Because you have already studied the same concept in your UG. And next, coming to the new concept, it is power series. The meaning of power series is any expression which is of the form a0 plus a1 into z minus a plus a2 into z minus a whole square plus so on. Or we can write this is of the form summation n is equal to 0 to infinity an into z minus a power of n. So an expression of this form is called as power series. An expression which is of the form is called as power series in terms of z minus a. Fine. Hence, a is a fixed complex number. Here, whatever the coefficients you have, it is a fixed complex number and it satisfies certain properties. So let me explain those properties. I'm just repeating once again. Power series is an expression which is of the form summation n is equal to 0 to infinity an into z minus a power of n. So when you expand this, you will get this. We say this is a power series which is in terms of z minus a, where all the coefficients a0, a1, a2 are a fixed complex number. And moreover, they are satisfying the following condition. First condition is that the series is convergent to a0 for z is equal to a. This series is converging to first value a0 for whenever you are going to choose z is equal to a, it converges to a0, right? Why? Because when you choose z is equal to a, all this term will goes to 0, right? So only left thing is a0. So this is the first condition. And the second condition is that if first value, that is a0 value, is equal to 0, then the power series become a1. If a0 is equal to 0, I can write this as a summation n is equal to 0 to infinity an z power of n. If all the values, a values, I'm sorry, it is not a0. If a is equal to 0, I can write this. That is, this expression become a0 plus a1. Since a is equal to 0, I can write this as a1z plus a2z and so on. I can write the same as summation n is equal to 0 to infinity an into z power of n when a value is equal to 0. And one of the easiest example in power series is a geometrical series. That is an into n is equal to 0 to infinity zn. So this represents a geometrical series as well. In the sense, when you're going to take an outside, you're going to get this sequence. Right? I'm sorry, this series. Why? Because we have a sum. Whenever you have sum of the sequence terms, we can say this is a series. So this is a geometrical series, one of the simplest power series it is. Fine. And moreover, if you're going to take this modulus, magnitude of this z value is less than 1, then I can write limit n tending to infinity, z power of n will be equal to 0. And moreover, if this is the case, I can say from the above condition, a geometric series is convergent. Right? Why? Because it is converging to certain value. Whether it is 0 or any value other than 0, it doesn't matter. See, if mod z is less than 1, this value is equal to 0. Meaning is that this geometric series Zn is convergent. Fine. Suppose if mod z is greater than 1, then I can say limit n tending to infinity, this z power of n value will become infinity instead of 0. So then this series is divergent. As I already told you, when it is converging to certain, finite value, a series is convergent. Since it is converging to infinite value, so it is a divergent series. I'm just repeating once again. Suppose if mod z is less than 1 in this expression, this limit value of zn converging to finite value, whether it is 0 or more than 0 or less than 0, it doesn't matter. The series will be convergent, anyhow it is finite value. Suppose if mod z value is greater than 1, then limit of this z power of n will be equal to infinity. Then this series will become divergent. So this is the basics regarding a power series. Hope so it is clear. Now let me explain few more basic definitions. So definitions. First one is convergent pointwise. So I am pronouncing you a number of times. A sequence Fn is converging pointwise. Meaning of pointwise. What actually the definition? Suppose if we have suppose let me consider a complex plane C. Fine. So it is a representation of a complex plane. And let us take A is one of the set which is subset of this complex plane. And if Fn is a function defined from this set A to a complex number as a complex plane C is a function. You already know the basic definitions of function. If Fn is a function which is defined from a set A to complex plane, then this sequence Fn, it is function as well, also sequence, or else we can say it is a sequence of function. Sequence of functions which is defined on the domain A. Fine. Defined on domain A. If this sequence can be written as Fn of z right from n is equal to 1 to infinity. Why? Because this function is mapping from A to C. All the elements of A will be of the form z. That is x plus iy, right? Why? Because A is subset of C. So all the elements of A is z. So when you map this, you will get Fn of z, where n value ranging from n is equal to infinity, converging to everywhere for z belongs to K. Then we say Fn converge pointwise. In the sense, we say Fn, sequence of function Fn is converging pointwise. Pointwise only when if you're going to take these functions, sequence of Fn of z, if this is converging converging at the point each and everywhere, then we can say that the given function Fn is converging pointwise. So this is the definition of pointwise convergent. Fine. Or else we can say that if f of z, we can also, while solving the theorems or a particular concept, we can say also say pointwise definition as, pointwise convergent definition as, if f of z is a sequence, then we can write f of z as limit n tending to infinity Fn of z. That is, if this value is equal to f of z, then we can say Fn is converging pointwise to f. I'm just repeating once again. If Fn is converging pointwise to f, then we can write this statement. Or else we can say we can define a sequence Fn which is converging to pointwise to a point f only when if limit n tending to infinity Fn of z is equal to f of z. So if this condition satisfies, I can say a sequence Fn is pointwise convergent. Clear? And this is about pointwise convergent. And the next step is uniform convergent. Fine, I'll just write here uniform convergence. So we have two types of convergence, pointwise convergence and uniform convergence. So when I said Fn is converging pointwise to f, we have to apply this definition. You have to remember this. That is, Fn of z limit n tending to infinity will be equal to f of z. Whereas coming to the concept of uniform convergence, suppose if I have a sequence Fn which converges to f uniformly, then for any element z which belongs to A, we can write there exists an epsilon greater than 0 such that for all the integer values n, magnitude of Fn of z minus f of z will be less than epsilon. This is as per the uniform convergence definition, and this holds for all n greater than or equal to this integer value n naught and for all elements z belongs to A. When you understand these basics definition, then only you can understand the theorems. Please go through this concept once again. Uniform convergence in the sense, whenever you have a statement like Fn is converging to f uniformly, I can write this statement directly. That is, for any element z belongs to A, there exists epsilon greater than 0 which satisfies this condition. That is, magnitude of Fn of z minus f of z is less than epsilon. Whereas pointwise convergence in the sense, we have to apply the concept of limits as I told you here. So this is the definitions of pointwise convergence and uniform convergence. Hope so it is clear. So this is regarding power series. This is point-wise convergence of a given sequence given sequence. This is uniform convergence of a given sequence. And at the beginning session, at the beginning of this session, I have explained the Cauchy's sequence as well. Here it is, right? So you have to remember all these definitions. Whatever I have done in this session, it is very important, and moreover it is basics for you. If you understand these concepts well, then only you can understand further. So please go through this video clearly. Now let me explain one more important concept, and this will form the base for measure and integration, which you are going to study in your 4th semester. Fine. So it is called as limit superior. The concepts are quite abstract. You have no way, you have to go through this. Fine. So limit superior and limit inferior of a sequence. Fine. Limit superior and limit inferior. As the name itself indicate, the general dictionary meaning is superior in the sense highest and inferior in the sense lowest. Fine. Suppose if I have a sequence xn, which is of a sequence of real number, then limit supremum is, or limit superior. Limit superior is denoted by limit of superior of a sequence xn. See here, limit supremum of xn or limit superior of xn. It is also denoted by limit over bar of xn. That is limit supremum value of xn or limit superior value of xn. So one and the representation are same, and it is defined as infimum taken over supremum of xn. Infimum taken over n and supremum taken over all the values of k, such that k will be greater than this infimum value of xn. Let me take this as equation 1. This is the definition you have to remember. When I have limit supremum, this is the representation for supremum. Whenever I have limit supremum value, you can write this as infimum of supremum xn. So you need to remember this definition. It is important. Fine. Similarly, limit infimum is represented by limit inferior or infimum, one and the same. Limit infimum of or inferior of xn is defined by limit of xn, and is given by, it is also represented by this. Supremum in the sense you have to put bar above lim. You have to infimum in the sense you have to put below limit. Fine. So it is a limit infimum. It is represented by this, and it is defined as supremum of infimum. Supremum over n, infimum over k greater than or equal to n xn. Call this as equation 2. You have to remember these two definitions. Limit supremum is infimum of supremum. Limit infimum is supremum of infimum. Fine. And now suppose if I have a sequence an of countable collection of a sequence of complex or real number. This is for real number. Fine. Whether it is a complex or real number, then we can define first element of a sequence as supremum of all the elements x1s. As I said, it is a sequence in a complex plane. All the elements will be of the form x plus iy. So first element, if you are going to take supremum over all the elements, and second element say supremum over x2 to x3, leaving first element you are going to take all the elements. Similarly, when you are going to take a3, leaving second element you are going to take from x3. Fine. So this is the meaning of supremum. And let me take, when you're going to represent this, I can write capital A as limit supremum. Why? Because we are taking supremum here. So supremum of all the elements of sequence xn. Similarly, if I'm going to represent B1 as infimum of the element x1, x2, x3, and if you're going to take B2 as leaving first element, you have to take infimum over x2, x3, so on. Similarly, if you're going to take B3 as leaving second element, you will get x3, x4 and so on. Then you can guess that B will be infimum, or I can write this as limit infimum, in the sense you have to put bar below of a sequence xn. No need to put here, only for limit it is enough. Fine, let me take this as equation 3, equation 4. So you need to remember this concept. So it is called as limit supremum, it is called as limit infimum. Basic definition, these two are very important. These two you have to keep it in your mind. Fine. Now further we can say that limit supremum of xn is exactly equal to a if and only if for any epsilon greater than 0 and for a positive integer n, if it satisfies the condition xn less than a plus epsilon for all n greater than or equal to n. Second condition is xn greater than a minus epsilon for a sequence of values n. Sequence values n. That is, limit supremum will be exactly equal to a only when if for any epsilon greater than 0 it satisfies these two conditions. This is for set A. Similarly, I can define for set B as limit infimum. Set B is in limit infimum, right? So limit infimum of xn will be exactly equal to b if and only for any epsilon greater than 0 and for a positive integer n it should satisfy the condition xn greater than b minus epsilon, and x second condition is that x will be less than b plus epsilon. Fine. So for a sequence of values, this is for all n greater than or equal to n. N naught, let me take this as n naught. Why? Because n is already repeated. Fine. So only thing is, when you have limit supremum, you have to remember these two conditions. It is just a reverse. You can note that. Fine. So these are the basic definition regarding a limit supremum and limit infimum. Anyhow, I'll send you the notes, but you just go through this. In this page, you have to remember these two concepts and these two definition. Clear? So this is the concept of limit superior and limit inferior. Now coming to the properties of limit superior and limit inferior. Rather than this definition, we are going to use the properties in almost all the theorems. You just see the property. Suppose whenever you have two sequences, then if you are going to apply limit superior, this represents limit superior. Limit superior of those two sequences is always less than limit superior of individual. In the sense, if you are going to split this limit superior, you have to put less than or equal to. Similarly, if you are going to split limit inferior, you have to put greater than or equal to. These symbols you have to remember. I am repeating once again. Whenever you have limit superior, you have to, when you are going to split it for two sequence, you have to put less than or equal to. Similarly, whenever you have limit inferior, when you are going to split it as two terms, you are going to write it as greater than or equal to. Fine. And limit superior of negative value will be negative of limit inferior. You can note the lines here. And exact reverse, that is limit inferior will be equal to negative of limit superior. That is, whenever you have negative value, this superior will become inferior and inferior will become superior. One and the same. Fine. And further, if you are going to add two individual limits to inferior value, since I have a bar below the limit, so it is limit inferior, can be written as less than or equal to those individual. Fine. And whenever you are going to add limit superior, individual limit superior, again you will get the less than symbol only. Only difference is when you are going to take total into two terms, then only the symbol changes. But here, whenever you have such kind of condition, these conditions will be same. So you have to remember all these six properties. These six properties are important for the further proof. So this concept is regarding limit superior and limit inferior. So hope so it is clear for you. So in the next concept, I will start with the very important concept, that is, in the next session I will start with the very important concept. It is radius of convergence. So thank you. Continue in the next session. And the notes will be forwarded in the group. Please copy the same.